Today we are going to discuss about this paper called Multimodal Few-Shot Learning with Frozen Language Model. So the idea is about using frozen language models and transfer its few-shot learning ability to a multimodal setting, vision and language. Okay. So they present a model method called Frozen, a method for giving a pre-trained language model access to visual information in a way that extends its few-shot learning capability to a multi-shot setting, multi-model setting without changing its weights. Okay. So this is like a brief picture of how the model looks like. So the language model is frozen, and they add a vision encoder, and in this this is entire thing is frozen, the model frozen, and this frozen model is trained on image and caption pair dataset, and only the vision encoder is trained. All of them are kept frozen. And once they have this trained model, they test it whether this is good for task adaptation. So train it on one dataset and then test it on another dataset, and whether it has encyclopedia knowledge capability. So it will be trained on a dataset where it needs more information, more knowledge than usual, and how this model is going to work there. And the third is fast concept binding. So they're going to give some pairs of images and the label, and they're going to test if the model is able to capture that relation. So this is how the frozen model looks like in the inference time. So one pair of image and the caption, which includes a question and an answer. This is one shot, and if you have few shots, then it will be like multiple pairs, and for each pair there will be a vision encoder through which this is for inference time. So for each image you will get some image prefix. Okay. So there are different ways they define this frozen model. Frozen could also be considered as a type of image conditional prefix tuning, in which this continuous prompt is not a bias but an image conditioned activation produced by an external neural network. Okay, so it's a continuous prompt and it is conditioned on the image, on the input. So you can also say it as dynamic prompts, which they explain it here. So the frozen extend the prefix tuning approach by making this prefix dynamic, in that it is not a constant bias but an input conditional activation emitted by the neural network. Okay. So there are different parts to the architecture. One is the frozen model. So they used auto-regressive language model, which is trained on 7 billion parameters on C4. It's a 7 billion parameter. The second component is vision encoder. So this is based on ResNet 50 architecture, and it's you can define it as a function that takes a raw image and emits a continuous sequence to be consumed by the transformer. Visual prefix, it's a linear mapping that mapping the vision encoder's output to this much channel. Okay, so it's kind of a projection from the output of the vision encoder to n embeddings with d dimensions. The idea is to make it consistent with the text embeddings, right? So they can be concatenated. So for training, only the parameters of the vision encoder is trained. So now we have the architecture. So architecture is like the same vision encoder, and we have language model, and you give this image here and the text embedding here, and you get the output, right? So for the training, they only update the parameter for vision encoder, and so what will be the output? So they are gonna give, so the input will be like this. There is some sub shot like image caption, image caption, image caption, image caption, and then there is image caption, some question, and this will be the y. So y is conditioned on the prefix, visual prefix, and the caption embeddings, right? So this is for image, this is for the text. So there are a few terms like task induction is the instructions. Please answer the question. So this is like induction, task induction. And suppose there is inner short. Inner short 1 means this is a pair. This is also a pair. So this is short 1. This is short 2. And there are no repeats, right? This set is not the same as this set. There is no repeat. If this set and this set are same, then it will be 1 repeat and 1 short. Okay, so repeat represent the repetition, short represent the number of unique samples, and ways represent how many unique samples we have in 1 shot. Okay, so those are the number of terms. Now for the experiments, there are three things they want to test it on. One is how well it adapts to the frozen model adapts to a different task. So we remember that frozen model was trained on image caption dataset. So now this is tested on visual question answering. So here this represents different shots, n equals to 0, 1 and 4. Frozen is their model where only vision encoder is trained. Frozen scratch is when the entire model, vision encoder and language model is trained. This is visual encoder and this is fine-tuned. Language model is fine-tuned. Train blind is they train the frozen model but they blank out the images. So it's more like prefix tuning. So there is no image but the prefix is tuned. Okay, so this is train blind. And frozen VQA is when the frozen is also trained on VQA dataset, and frozen is the blind version of that. This one, this represents if VQA dataset was used for training or not. So what they're so the results are that the frozen performs better than the scratch fine tune. So it's kind of interesting to see. And also, like they conclude is that the frozen model has a greater generalization capability for task adaptation. And also, like with increase in the number of shots, it does improve. So they have two conclusions here. First, they show that training a visual encoder through a pre-trained and frozen language model results in a system capable of strong out-of-box zero-shot generalization. Second, they confirm that the ability to rapidly adapt to a new task given appropriate prompts is inherited from the pre-trained language models and transferred directly to the multimodal task. The second thing is they wanted to test about the encyclopedian knowledge. So here we study the extent to which frozen can leverage the encyclopedia knowledge in the language model towards visual tasks. Okay. So for that, what they use is this dataset, and it's a visual question answering dataset designed to require outside knowledge in order to answer correctly. And here again, the fine tuning performs worse than leaving the model frozen in terms of generalization performance, and we can see it here. It's kind of have the same kind of trend. It increases with the number of shots and it's better than the other models. 400 is the another version. Here they use 7 billion parameter model, and here it is 4 million. It's just to see if the size creates any difference in the performance. The third and last thing they want to test is fast concept binding. So in multimodal setting, fast binding refers to the model ability to associate a word with the visual category in a few shots and immediately use that word in an appropriate way. Okay, so for that they use two types of things. One is open-ended one is this dataset and another is fast QVA. So I'll give you a brief of how these two looks. So for the first one, this is for fast binding. So what they're trying to do is have some samples, few shots with some name, random names, and what they want to see is if the model can uh, bind this lion to this concept. Okay. So they have 1 shot, 2 shot, 3 shot, and so on. So this is for the open for the first task, and for the second one it's a little bit trickier than the first one. Here there is one, this is the item 1, this is item 2, and there is some question. So rather than asking what is this, they are asking what is the DAX made of. So it's a more challenging data set. Okay, so this is and there are 2 versions for both the tasks. When it is random name, it is just fast the name, and if it is replaced by the actual name like ways and table, then it is called real name. So let's go to the results for these. So the model performs, so the way to read it is, this is inner shot, how many shots are there and how many repeats are there. And frozen is the first task, and frozen is the real name where the random names are replaced by real names. So we expect that to work better because the language model has been trained on real names. And it does perform better than the baseline, not on the baseline, but so none of the method performs better than the baseline. So that's the paper claim that there are still a lot of research has to be done to make the multimodal to make the frozen language model to work in multimodal setting with few shots. So here what we can see here is with the number of shot, it does increase a little bit but not much. So I don't know how much it's the shots are important. So this is for 2 ways, there are 2 classes. This is for 5 classes, the random is 20%, and here also it's the same. It does improve. So this is like the prefix tuning, and this is like with the visual encoder. So it's better than the prefix tuning. They also explain that when you have multiple classes, so instead of just having lion and cat, they have lion, cat, dog, and 2 more. Okay, so this entire thing is 1 shot. It decreases, so it doesn't work well. Frozen is not significantly above chance. This shows that learning to bind 5 new names to 5 visual categories in a single forward pass is beyond the current capabilities of frozen. Let me remind what these 5 things mean. So for example, this is lion and dog, this is 2 ways, and if I have multiple 1, 2 and even 3 different things in 1 shot, that becomes 5 ways. Okay, and this is for the fast VQA, and we expect that the frozen the entire thing performs less than the last task, and it also has kind of same trend. So the limitation of frozen is that it achieves far from state-of-the-art performance on the specific task. It learns it learns in a few shots compared to a system that use the full training set for those tasks. Okay. So in conclusion, they presented a method for transforming large language model into multimodal few shot learning system by extending the soft prompt philosophy of pre-tuning to order set of images and text while preserving text prompting abilities of the language model. So for more details, you can read about the paper. Thank you.